Hello, everyone. In this video we present Pure, a method to solve the data-free meta-learning problem. This work will be presented at CVPR this year. Let's begin with the problem definition of data-free meta-learning. The goal of data-free meta-learning is to enable efficient learning of new unseen tasks by meta-learning the meta-knowledge from a collection of public pre-trained models without access to their private training data. In this work, we propose an architecture, dataset, and model-scale agnostic framework named Pure. Pure consists of two novel techniques, episode curriculum inversion and inversion calibration following inner loop, to achieve efficient meta-training and alleviate task distribution shift, respectively. We also propose 3 real-world scenarios for comprehensive and practical evaluations of DFML algorithms. Extensive experiments verify the superiority and broad applicability of our method to real-world scenarios. Given a collection of pre-trained models of different tasks, what kind of information can we obtain? A recent work of data-free meta-learning only focuses on the limited information of model parameters and architectures and achieves unsatisfactory performance. Besides, it can only apply to the specific scenario where all pre-trained models are small-scale and with the same architecture. In our work, we try to design an architecture, dataset, and model-scale agnostic framework by exploring the underlying data knowledge contained in numerous pre-trained models. Let's dig into our method. During meta-training, we progressively synthesize a sequence of pseudo-episodes by distilling the training data from each pre-trained model. Thanks to the episode curriculum inversion technique, we adaptively increase the difficulty level of pseudo-tasks according to the real-time feedback of the meta-model. During meet testing, we further propose a simple plug-and-play supplement, inversion calibration following inner loop, to narrow the gap between meta-training and meta-testing task distribution. We formulate the overall learning objective of our proposed Pure as an adversarial form in an end-to-end manner. We search for the optimal meta-model by minimizing the expected meta-learning loss, while we update the pseudo-dataset to synthesize harder tasks with higher quality by simultaneously maximizing the meta-learning loss and minimizing the data generation loss. During meta-training, we update the pseudo-dataset to better image quality by minimizing the classification loss plus additional regularization terms. We adaptively synthesize harder tasks by maximizing the meta-learning loss controlled by the real-time feedback from the meta-model. Thanks to the curriculum mechanism, we progressively synthesize harder tasks which have not been learned by current meta-model, thus achieving efficient meta-training. During meta-testing, we propose a plug-and-play supplement to narrow the gap between meta-training and meta-testing task distributions. We enforce the backbone to extract similar features for both pseudo and real data by minimizing the contrastive loss, thus alleviating task distribution shift caused by the gap between the pseudo and real data. For comprehensive and practical evaluations of data-free meta-learning methods, we propose 3 real-world scenarios, SS, SH, and MH. Here are some quantitative results on these 3 benchmarks. Our method can simultaneously apply to all 3 real-world scenarios without any change and achieve significant performance gains compared with existing baselines. Now, let's have a look at some qualitative results. First, we visualize the pseudo-tasks inversed from pre-trained models with heterogeneous architectures. As we can see, useful features like texture and shape can be inversed, thus benefiting the meta-learning process. We also visualize the embedding space and the pseudo-tasks at different meta-training iterations. We observe that the harder tasks are with more blurry decision boundaries. Thanks a lot for watching.